Today's lecture is about sampling distribution and central limit theorem. They are quite really important topics, so I'm gonna cover those today. And central limit theorem is one of the most important theorem in modern statistics. So in statistics, we really want to do inference, and what we want to do, the goal of statistical inferences include this: how to draw conclusions about the population, because we cannot, for example, if we do the survey, we cannot do the survey for every people in the population. So we can only use the subset of the population. So we call this as sample, right? So using sample, we want to know something about population. And how to estimate population parameters. So we call the value for population as parameter. We learned about that in previous lecture. And we also want to quantify the amount of confidence. That means, in other words, we want to quantify uncertainty or confidence. We want to quantify that. And also we want to use this information to make decisions, binary decision, yes or no. So make decisions. And before we delve into this statistical inference, we need to know this notation. One is population. You already learned this. So entire group of items or individuals we want information about. And sample is the part of the population we actually examine in order to gather information. And a parameter is about the population, number for the population, and statistic is the number that describes the sample that we have. So this is the slide we saw before, populations and parameters. So we learned about population parameters, we use Greek letters. And for sample statistics, we use these alphabetical letters. And a parameter is defined as a fixed number, but we don't know its actual value because it's about population. We don't have any information. We don't have the full information about population. That's why we need a sample and statistics. So the value of the statistic is known after we take the sample. So it's about sample, and it can vary from sample to sample. And we often use this statistic to estimate an unknown population parameter. That's all about the statistical inference. And we are going to learn about statistical inference of proportion and mean. And in the next 3 lectures, I'm going to talk about the statistical inference of proportion, and after that, we are going to talk about the mean. So statistical inference really about the drawing conclusions about population using the sample, but we also really need to quantify how much confidence we have about that conclusion. And we are in particular interested in what proportion of the population has a certain opinion or trait, and as well as the mean value of a certain variable. And I'm going to use this as an example. That is approval rating, GGU. The question is, what proportion of Korean residents support the current president? So let's say if we really want to know the proportion, the approval rating, this is an actual procedure, like randomly sampling a small number of people compared to the population and ask them if they support the current president or not. And this is actually the simple random sampling, right? Just randomly sample part of the population. And let's say you did this and then you found 690 people out of 1,000 people showed supports. That means 69% approval rating, right? And in this example, the proportion of the population is denoted P, that is parameter, so there's no hat, just P. And then the proportion of the sample is written P hat, that is statistic. So in this example, the count is 690, that is another statistic, and P hat is 0.69. Then we don't know about P, it's unknown, but P hat, as you saw, P hat is 0.69. But we can use P hat to estimate P. That's the goal. But the other survey, let's say you repeated this survey again and again, and then you got this time 0.72, and next time 0.68. That varies. And we can actually simulate the whole Korean population because using the programming language. For example, let's say this is the parameter for the real approval rating, 0.71. This isn't, we don't know this value in reality, but let's assume that I'm God. so that I know the approval rating, so actual number. So I know it. I know 0.71. That is 71% people of the Korean population support the current president. And then I actually created a population, the vector for population. This is actually 51.225 million people. And zero means no support. And I made it, some of them as one. One is support. In this MATLAB programming, I made this number of people, this times 0.71, then made them as one. Okay. So then now we have the whole population, the truth, ground truth, and then in this simple random sampling iteration, I'm gonna do the sampling. Basically, sample 1,000 people from that whole population each time. But I calculated the proportion of the sample, the support, within that sample, and I repeated that 1,000 times. So here, important thing is each sample has 1,000 people in it, and I repeated it 1,000 times. Okay. That means I have 1,000 samples, and I have 1,000 p hat values. And because there are 1,000 values, I can draw the histogram. That is this distribution. This is a sampling distribution of a proportion, and I can calculate the mean of the p hat. So this is p hat and p hat, mean and standard deviation, and mean is 0.71. Interestingly, I didn't say each sample that the mean is 0.71, but the mean of the samples gives us the ground truth value, 0.71. Because this is a sampling distribution, the distribution of the samples, there is a standard deviation. So I'm going to talk more about this in a minute. And this is a sampling distribution, and it's different from sample distribution. It's super important to know the distinction between these two. So sampling distribution is the distribution of the sample statistics from many samples. So this is a distribution of samples, and this is actual distribution of the data within one sample. That's sample distribution. This really shows the data, but it shows the summary statistic, the distribution of the summary statistic. So they are different. Okay, so in practice, we only sample the population once. Usually, we can sample multiple times, but usually if we do just one study, that is one sample, right? But here, we want to understand what would happen if we sampled that population repeatedly. So that's really the sampling theory. We want to know the values that statistic can take and how often it takes them. That is a distribution. So that is the distribution of the statistic. So as I said, statistic is a summary value for each sample, and the distribution of the statistic is the sampling distribution. And this will give us an indication of how well a statistic estimates a population. The sampling distribution of a statistic is the distribution of its value in all possible samples. Let's say these possible samples of the sample size of the same sample size from the same population. So let's say you have the 100 n equal 100 sample, and the sampling distribution is, let's say you keep sampling this size of the samples, so 100 samples from your population over and over, and you draw the distribution. That's the sampling distribution. And sometimes we talk about unbiased estimate, and we say a statistic is unbiased when the mean of its sampling distribution is equal to the true value of the parameter. Then we can use normal model to model the sampling distribution, and to do that we need two parameters, mean and standard deviation, because normal model is always described with the mean and standard deviation. And in the same simulation, we did, we know the mean, that is p, but we cannot know the standard deviation until we do the simulation. And how can we know the standard deviation mathematically? And for the proportion, it's kind of simple, because from the binomial model, we know the standard deviation of the number of an outcome. And that was square root of MPQ. You learned this. And then, because we are dealing with proportion of the outcome, we just divide that by n. and that becomes square root of PQ divided by N. So the sampling distribution of a proportion can be modeled with a normal model, with the P as a mean and square root PQ over N as a standard deviation. And I will show you how this is correct using the simulation. So in our simulation, we, given that we set up the population parameter as 0.71 and the number of samples was 1,000. And therefore, according to the model, the normal model, because it was PQ over N, that the calculated number from the normal model was 0.0143. Okay, this is just graphical view. And this is a simulation. Actually, given that we are doing the simulation, we can calculate the standard deviation empirically using the data we got. So in this time, I changed the N number. So sampling N, sample N, and then I calculated the standard deviation based on the normal model. So here, this is sample N when sample N is 20. So I'm kind of picking 20 people at each time, but 1,000 time iteration. And then the standard deviation becomes 0.1035. And then this is the based on the data, so it is data, but theoretical standard deviation is 0.1015. So very similar, right? And it increases as the sample number of sample increases, the standard deviation decreases. So as you can see, the theoretical, these are theoretical based on the mathematical model, theoretical number, and this is from our simulation, and they are really same, almost similar. And as you can see, as sample size grows, the shape becomes narrower. The values from the sample statistic becomes closer to the mean of population, the population parameter. So population distribution is really simple one. That is a probability model derived from the information on all members of population. And in our example, there is only yes and no, yes and no. And the individuals chosen at random from this population will follow the same probability model. When does the normal model work for sampling distribution of a proportion? And the sample size matters. So this is the P equal 0.5 and sample size N equal 2. So let's say you have the population probability 0.5, and then you get 2 data points at each iteration. And then the distribution becomes like this. It's similar to normal model, but not quite, right? So just say it's a discrete number. And in this case, P is very low, so 0.001, and N is large. In this case, it's still not normal model, right? Normal shape, normal distribution. It's a really skewed distribution. And you might remember that we talked about the approximating the binomial with the normal model when we can do this when NP, N times P, or N times Q is larger than 10. And this applies to this question in the same manner. So when the P and N times P is larger than 10, we can use the normal model for proportion. And there's another assumption in addition to this size. So that's independence assumption. That means the individuals in the samples must be independent of each other. And it's really hard to know if this assumption is true or not, but we can check the following conditions that provide information about the assumption. And the condition is randomization condition. So if we sample these samples randomly, for example, random sampling, we can make sure that the independence assumption is correct. And there is a 10% condition. The larger is not always better. So if the sample size is too large, so that that is larger than 10% of the whole population, then the remaining individuals are no longer truly independent of each other. So that sample is related to other samples. So the sampling distribution will have a smaller standard deviation. So the sample size should be less than 10% actually. But usually the population is huge. So this 10% condition is not that problematic many times. And there's a success failure condition that is same with the thing that I just said. The NP and NQ should be larger than 10. And I wanted to show the sampling distribution of a mean as well, because to give you a sense of how the mean is different from proportion. Actually, they are quite similar. And there's a simple simulation that the textbook provides. If we toss one fair die, 주사위, 10,000 times, what should the histogram of the numbers on the face on the die look like? And when we just get one number from one die, for example, 1, 2, 3, and then throw that, and then get the number on top of the face, and then that distribution seems a uniform distribution. That's basically the n equals 1 case. So get one number from each iteration. The process is throwing the dice. And this is 2 dice average. So you are getting 2 numbers. For example, in this case, you are getting 1 and 2, and 1.5 is the number from this sample. And it becomes more symmetric and becomes similar to the normal distribution. And when you throw the 3 dice and then 3 dice average, it becomes more similar to normal model, and 5 and 6. This is 20 dice. Yeah, so perfectly normal. So that means this is n equal 3 case, and 5 and 20, n equal 20. And if you have larger sample size, the mean of that sample becomes more normal, and then and also the mean of the distribution becomes unbiased estimate of the whole population. So 3.5 should be the mean of the dice, the average dice. So the sample size gets larger. Each sample average more likely to be close to the population mean, as you can see here. The distribution gets narrower. That means each time each data point from the sample gets closer, becomes more likely to be close to the population mean. Then you have the precision, better precision of the population parameter. And we see the normal shape clearly, and spread becomes smaller. So there is a reason why this works, and there is a central limit theorem. So what we saw with dice simulation is true for means for repeated samples for almost every situation. So in this case, in this dice case, the actual probability for each dice is uniform distribution. But if we get, so for each data point is really uniform distribution, but if we sum up many cases, many different data points, it becomes a normal distribution. So the point of the central limit theorem is, the definition is the mean of the random sample is a random variable whose sampling distribution can be approximated by a normal model, and the larger the sample, the better the approximation will be. And only assumption here is the independence assumption. And the important thing is this works no matter how the data are distributed in the first place. And this is proved by Laplace in 1810, very long time ago. And I'm going to tell you what does this mean in the next slide. So here, the important fact is it works regardless of the shape of the population distribution, even if we sample from a skewed or bimodal population. So this is an example of the CEO compensation data that I think I used before. And this is showing the CEO's salary distribution, and it's very right skewed, right? And then let's say we take the samples with sample size is 10 multiple times, 1,000 times, and the sampling distribution becomes like this. And if we increase the sample size, it becomes more normal and normal, right? And with the 200 as sample size, it became a perfectly normal distribution. This is the central limit theorem. So no matter what was the underlying distribution of the original data, so like this, original data point, the population distribution, if your sample size is large enough, the sampling distribution becomes normal distribution. I'm going to show you the bimodal distribution, how it works. So I actually did a simulation. I'm going to upload all the codes, the MATLAB codes, to our GitHub repository, so you'll see all these codes there. So this is the bimodal distribution. I created that using this. Two normal random numbers from normal distribution. And I'm kind of using the different sample size, 10, 30, 60, 100, and I sample the iteration is 10,000 times. And as you can see here, if the sample size is small, it's still bimodal. Okay, so this is 30. 30, it becomes a little similar, more closer to normal distribution, but not quite yet. But if you have 60 and 100, it becomes perfectly normal distribution, right? So it works. Whatever distribution was for the original data and population distribution, the mean of the distribution of the mean of the distribution of the mean of samples becomes normal distribution. This is the magic. And because of that, we can use many different types of statistical methods on the data. And which normal? What kind of normal? Because we need to know the mean and standard deviation to use the normal model. And mean is usually for mean, that is population mean, mu. And standard deviation is, as you saw, the sample size becomes larger, the standard deviation becomes smaller. And how smaller? How much is smaller? The good news is the standard deviation falls as sample size grows, but bad news is it doesn't drop as fast as you would like. So this is a standard deviation of the sample mean. So y bar is sample mean, not the parameter. That is not mu. So this is about sampling distribution, right? The standard deviation of the sampling distribution, and that is defined by sigma, that is standard deviation, sample standard deviation, population standard deviation, and divided by square root of n. So this standard deviation is called standard error of the mean. We are going to talk about that in later lectures multiple times. So don't worry if you don't totally get this. But this is really important value. You might see this standard error of the mean. We call it SEM many times, and you will see that that acronym in papers, many kinds of papers. We always report that SEM number. Okay, so which normal? For proportion, mean is, so mean of the sample proportion is P, proportion, population proportion, and standard deviation of P hat is PQ divided by N and square root of that. For quantitative data, a sample mean is y bar, and the mean of y bar is mu, that is population mean, and standard deviation of the sample mean is defined by sigma divided by square root of n. Okay. So let's summarize. The statistic itself is a random variable, and a different random sample would have given us different statistical results, right? That generates the sampling distribution, right? The statistic, I'm repeating that, statistic itself is a random variable. You are getting different values each time. So that's the definition of random variable. Have the probability and getting different values for each time. And this sample to sample variability is the sampling distribution. Okay. And fortunately, for the mean and proportion, thanks to the central limit theorem, we can model this sampling distribution using normal model. So when it becomes to the normal model, it becomes really easy. So let's summarize again. So let's say we have this population distribution. This is population model that we cannot observe. Actually, we don't see this ground truth. But let's say we have this value, and then we draw samples from this. Like this is one time, so sample one. Let's say this is our study, and we got one sample, solid line, and size of n. For example, let's say we have 100 people data, subjects data, and we got the histogram and summary statistic. So this one value, just one data point. But let's say we assume that we repeat this process again and again. So this dashed line says us the imaginary samples from the same population model, and then it will give us a y bar 2, y bar 3, and then after we got multiple values of this sample mean, we can get this sampling distribution. And this sampling distribution, according to the central limit theorem, the shape of this histogram, if we have the samples large enough, we can model this with a normal model using this equation. Okay, so this is the summary. If you understand what's going on here, you achieved the goal for today. But so this is for the next class, but we cannot really know the mean and standard deviation of the population, and therefore we don't really know the mean and standard deviation of the sampling distribution, right? Then what should we do? So that's going to be continued in the next class.